So 5B is going to be a short lecture to sort of combine the ideas into this thing that I call data charts, where we have information about, let's say, the people that work in a particular store, and we want to do some questions that ask probabilities that certain people will have characteristics that they describe. So in this list it says a store employs cashiers, stockers, and deli workers. And this chart shows their distribution. We have cashiers, stockers, and deli workers. And then we have the fact that they're married or not married. And we're going to go through and ask questions about probability, which will always tend to be based on the same numbers of total people working in the store, and try and find out what's the probability people fall into a particular category, or perhaps one category, or maybe both of two, or whatever it's going to be. So we want to look at that when this chart information comes to us. So what I find helpful in something like this is to get some totals to work with. So here we have, if we want to get the total of all the people that are married, we would add 10 and 20 and 54. 10 and 20 will make 30 and 54. This will make us have 84 people as a total. How about people that are married? Let's take 68 and 17, which will get me to 78, 85. And then add the 75, which will get me to 150, 160. And we have these other totals, which are where we only add two numbers together to get these totals over here. $10 and 68 for 78. 54 and 75, 129. And 20 and 17 for 37. Now this adds fairly easily 80 to 64 for 244. That same number should be the totals of what we get here. 78, okay, we take it into 198, 207, and then 237, 244. I get 244 grand total people working in this store. But the blue ones that I've added are totals that might be helpful. The 244 is definitely going to be helpful. So what we want to do here is we're going to work on that concept of or, maybe not or, but anyway, whatever concept we have of finding percentages or decimal values for the likelihoods, we'll set them up as fractions. Find the probability that an employee is a cashier or not married. So we'll get the cashiers, right? With the cashiers, we got 10 and 68 for 78 out of 244. So 78 out of 244 cashiers. Or not married. So not married, we have 160 out of 244. But is there any overlap? In other words, are these sets having overlap or are they disjoint? And let's look at the numbers that we get when we look at all of them. This might help understand how that or value works. When we got the total of the cashiers, we did this 10 and that 68. When we went for the married, we went for that same 68 and the 17 and the 75 that are up here. So this 68 represents cashiers that are not married. But those hit that category twice. So if we add these up and get 238 out of 244, we overcounted by some. So in this case, I'm going to look at this 68 right here, and I'm going to subtract that 68 over 244, and that way I don't have to decide. Do I only want these 10 and that 160 to get me 170? That was kind of an easy, lucky way the numbers worked out. Or do I want this 78 and that 17 and that 75? So if I go for this 78 and 75 is 153, 163, 170. Looks like I'm going to get 170 out of 244 that way. Or if you remember this way, I got all that 160 and these 10 other cashiers that were not married getting 170. But let's look at what happens with the two black numbers. 78 and 160 gets me the inaccurate total of 238. And then when we subtract the 68, or if you want to say, I'm going to add up these four numbers, 10 and 68 for 78, and 75 for 153, and 17 for 170. Again, you'll get to 170. Look where this takes us. Take the 238 minus the 68, you're going to get 170 over 244. So we're looking at this chart and its representation of why these are not disjoint. For A, it's those 68 non-married cashiers. Now, we've got part B and C on the same chart. So I want you to be able to go back to this and get a few different pieces of information as you're looking back on how we use these charts. A stocker or married. Okay. So when we go for the stockers, we can go for 129, and if we go for married, we can go for 84. But are there any married stockers, right? I am a stocker and I'm married. That causes them not to be disjoint. So these three numbers represent married people. This particular number represents married stockers. So, if we go for the first thing that it mentions is people who are stockers, we get 129, 244. Plus the second thing they mention is people that are married, which gets me this 84. And that's out of 244. And then I have to go back and I have to take away or subtract the double counted 54. So out of 244 this time, stocker or married. Okay, let me go down the stockers and get 129. And then this 10 makes 139, and that 20 makes 159. And that's where it's going to have to wind up being. How? Well, I did the stockers first, and then I added the two other kinds of marrieds. Or I could do the married first, 84, all these, and just bring in the other stockers, 84 and 75, and give me the 159, also that. Or if you want to look at the numbers that we have, 10, 54, and 20, okay, that made up the 84, and then bring in this 75. Add up those four numbers, we didn't hit the 54 twice. The way this brought it up was it brought up the 129 as your total of stockers, and it brought up your 84 as your total of all your married employees, and then went back and subtracted the overlap, which you can always do without having to make a decision or say, wait, how do you know which to do? You don't have to make a decision like that. Because what this makes is 213 minus 54 and that's going to make 159 as well, 159 over 244. Not married. They can also come at you and say, please just get me the percentage of people that are not married, or the decimal value, or even the fraction of not married. So the not married total is 160. Out of everyone, 244. All it says is not married, so you want everyone that's not married. You certainly could have come along and added them up again, gotten 68 and 75 for 130, 143, 153, 160. You could certainly get them that way as well. But there's no subtraction because there's no overlap. There's no overlap when you have only one characteristic. But recognize that one other thing they could have asked, and I'll add that here, is question D. A cashier or a deli worker? But a hand usually shoots up at this point. Can't someone do both? Okay, yeah, that's tricky. What they probably do is determine where they make the most money or where they put in the most hours and define each person as only taking one slot. So that's why they don't necessarily want to do this. But if they are considered disjoint sets, so that no one does both jobs or no one is defined as an employee who primarily does both jobs, then we would be able to go ahead and do D, which is 244 total. And we get our total cashiers, 78. And our total deli workers, 37. get 115 over 244. Because they're disjoint sets, we don't have to subtract anything. Even though it's two sets, they're disjoint because if you're here, you're not there, and if you're there, you're not here. You only have one place to be. But that can get tricky because of that whole hybrid person who does both, and they got to make sure they don't double count the same person. So they don't always go like that, but the idea is here, this data can be sets that I like to view as parallel, right? The way we get the numbers are parallel, versus a single set, where it's just one row or one column's total, or where they intersect. Because if you think about it, there's generally two kinds of lines when you're in a plane. Yes, they talk about when you're doing the same line, but I don't see that as two lines. You have parallel lines that never meet. That's no intersection. Those would be disjoint sets. And then you have intersecting lines, which is lines that cross somewhere, and those would be sets that are not disjoint. And we have a representation of each of those kinds up here. So that's enough for 5B to really close out that lecture and help you work on homework 5.